Hello everyone, and thank you for joining us on this installment of our Tech Tuesday series. My name is Dustin Kinsler. I've been an application engineer here at CamLogic for just over 10 years. Definitely more of an engineer than a presenter, so this might not be the most flashy presentation, but I'll be covering what will hopefully be some really useful information. Today we're going to be talking about poor scan data, why it happens, and what can be done about it. It seems like a lot of people have this idea that a scanner is some magical device that can take a picture of a part and give them perfectly accurate data that can then be brought into their CAD system, and they're done. In reality, a scanner is just going to give you a pile of measurements that you have to spend a bunch of time making something useful out of. How much time? That all depends on what I'd break down into three areas. Hardware, the scanning system you're using. They are not all created equal, and to a point, you get what you pay for. Anyone out there that thinks they can spend a couple grand on a system and check a surface profile within a couple microns is out of their mind. But the topic of hardware is a presentation of its own, so we will not be covering that today. It's important to do your research when getting a system. The most expensive does not necessarily mean it will be the best for your application. That said, we'll be sticking to things that can affect your scan quality. So, environment and material properties. So you might be asking yourself, what is crappy scan data? And that's really going to depend on what you need to do with the data. I would consider this crappy data if I was planning to create an A-class surface. But it still might be perfectly acceptable if you're just trying to create a visual representation for, say, an animation. This is data from a laser line scanner, just like a typical portable CMM with a laser scanner on it. There was no processing done to this other than just creating a triangulated mesh. Those of you who have used scanning systems have or will see something like this to some degree. Now, most of this can be fixed with a post-processing software, but let's go over the things that can cause this. Let me start by saying no, coffee is not a problem. Otherwise, they wouldn't even allow me near a scanner. What I'm trying to point out here are your environmental variables. Where are you scanning? Are you right next to a press? Maybe a forklift keeps driving by? Anything generating vibrations has the ability to affect the quality of your scans. Vibrations are movement, albeit very small, it is still movement. Movement that your system cannot compensate for. It is ideal to set up away from areas where a lot of people will be. Sooner or later, someone will bump the system, causing more uncompensated movement. Lighting can also affect your scans, especially sunlight. Any vision-based system is going to utilize some sort of camera and a light source. If either of these are overpowered by the ambient light, the system will either stop capturing or create unreliable data. So next up is temperature. I'm not going to read all this as it's just copied right off of Wikipedia. You just search ISO 1. This is the first result. Basically, ISO, the International Organization for Standardization, says all measurements should be taken at 68 degrees Fahrenheit. If you take a look at your certifications on your scanner, it will more than likely say it was calibrated at 68F or 20C. This pertains to all measurements, be it a CMM, calipers, or a 3D scanner, as 3D scanners are nothing more than a measurement device. That being said, here's some more info to chew on. Your machine all by itself can be perfectly in spec at 110 degrees as long as it was calibrated at that temp and the artifact used for said calibration was at its correct calibrated temp. And the room and the temp of the room / device stays the same. Anything you measure that has thermal expansion capabilities, everything in other words, will change its true shape though at that temp. and your real-world readings will be skewed. So let's say your scanning area is 60 degrees in the winter and 75 in the summer. And let's say somehow you're actually calibrated at those temps. A good part in the winter could be too big in the summer, even if they're exactly the same. This is something that should definitely be considered, but with the typical accuracies associated with scanning, most are not that concerned, especially if you're just scanning to do some sort of reverse engineering. Temperature stability, on the other hand, is very important, if for nothing other than just to reduce the amount of work it takes to get a nice model. This simply means let the system warm up to its full operating temperature. This temp will vary from system to system, but for example, two of our scanners, one is typically 15 degrees C over ambient, and the other is 8 degrees. So does this mean nothing should be scanned outside of a lab setting? No, but these are all variables that can add to the level of uncertainty of your data. And you have to decide if the risk outweighs the reward. Of course, a lab setting is going to be the best, but sometimes it's just not necessary or feasible. In the end, it's up to the user to make that call. Hopefully, understanding the risks, he can make an educated decision. Now we'll move on to material properties. With all optical methods, reflective or transparent surfaces raise difficulties. Reflections cause the light to be reflected either away from the camera or directly into its optics. In both cases, the dynamic range of the camera can be exceeded. Transparent or semi-transparent surfaces also cause major difficulties. Double reflections and inner reflections can cause the stripe pattern to be overlaid with unwanted light, entirely eliminating the chance for proper detection. Reflective cavities and concave objects are therefore hard to handle. It is also hard to handle translucent materials, such as skin, marble, wax, plants, and human tissues, because of the phenomenon of subsurface scattering. You know, there's a lot of terms here that you might not be familiar with, but simply put, shiny stuff and anything that the light can penetrate will negatively affect your scan data. These are all variables, and we should do our best to remove as many variables as possible. Depending on your scanner, some of these may not be a concern to you as much as others, but no matter what, all of these will have some influence. So now we know some of the problems. What can we do to solve them? Well, a lot of the environmental things, you're just going to have to do your best to avoid them. But your first step in the direction of quality is simply to calibrate. Calibrating at the full operating temperature is critical. Make sure to calibrate all of the components following the manufacturer's specifications. This will ensure you're collecting the best, most accurate data your system can produce. Some systems will have multiple calibrations. A lot of the laser scanners do. One for the laser scanner and another for the locating device, such as the arm or laser tracker. The proper calibration is going to ensure that the laser or the camera is properly detecting the projected light, and the system is placing that collected data in the correct XYZ location. Surface prep will also greatly help with data quality. Remember, scanners don't like shiny or transparent materials. Some manufacturers state that their system can handle those without a problem, but I can tell you from experience that even if they can, it's still better to apply something to the surface to dull it. Scanners like matte white. White allows for a shorter exposure time, meaning you can scan faster, and matte will allow for a clean and clear reading of the projected light, reducing the quantity of noise data. A simple application with the old rattle can flat paint can achieve this. But for those of you who don't want a permanent application, it's common to use a liquid penetrant inspection developer, such as Magnaflux SKD S2. There are now even sprays specifically sold for our application of 3D scanning. So let's say you've taken all the precautions possible and you're still ending up with data that looks like this. And it's completely possible just due to the inherent inaccuracies of the system. Like it or not, no measurement system is perfect. And all of the things we've covered so far can only reduce error. Nothing will completely remove it. A post-processing software, something that was designed to work specifically with scan data, is about your only option once the data is collected. Some systems will come with software that can clean up, some don't. And of the ones that do, some are decent, some aren't. I would highly recommend specialized software. It can make the difference between a useless gadget and a critical tool in your process. But back to our data. A lot of the issue here is layers of data, gaps from one scan pass to the next. How can this happen? Well, let's say, for instance, your scanner has an accuracy of plus or minus 150 microns. You take 2 scan passes on a surface. Here's the result. First scan pass is teal, second one's purple. Your 150 micron accuracy means you have the capability of a 300 micron gap. This is obviously worst case scenario and highly unlikely, but the point is it can happen. Now, before you go freaking out that this is crazy inaccurate, I'd like to point out the sizes that we're working with here. A lot of people have seen this or something similar, but looking at this, the biggest circle being the exaggerated diameter of an average human hair, this should put things into perspective. Your tolerance is plus or minus a hair and a half, or just over 21 red blood cells. Getting back to our problem, if we take it a step back before creating that mesh, we have just a scanned point cloud, just millions and millions of XYZ location. Most softwares out there will allow you to keep the points grouped by scan pass. In other words, the software will create an object of points for every press of the scan button. Here's the same data with the individual scan passes highlighted. This will allow you to globally optimize the data by registering from one scan pass to the next, removing or at least minimizing the gaps. This is a process already done for most structured light systems, whether the user knows it or not. Structured light or white light, blue light scanners typically don't have a locating device like a laser scanner, so they rely on either referent targets or dot stickers or overlapping data. If it's the latter, there needs to be features that can control the fit between scan passes. So just like structured light data, we can use the overlapping data from one scan pass to the next with our laser data. After we run this registration algorithm, our data looks like this. The sort of fuzzy looking blurring of colors is actually a good thing. It is the 2 scans showing through each other where they intersect. Now if we run our merging STL creation step on this data, we get this. Granted, there's still some holes in the data, but those can easily be taken care of. But otherwise, this is much cleaner and therefore will be much easier to work with down the line. But do remember, we just moved the data to get this cleaner data. If your scanning practices are not up to par, we could have just made this car bigger or smaller. But this will still work better for most surfacing applications. With that, I would like to say thank you for stopping by and have good luck with your scanning data. Thanks.